My name is Russ Lakis. I'm a software engineer at Ophir Spiricon in Logan, Utah. We're the beam profiling division of Ophir, handling all the Spiricon and photon beam profiling products. And today we're going to be looking specifically at some of the basic software features within the BeamGage camera-based profiler. The objectives of today will be to review camera settings and how to use them, how to acquire useful laser profile data. This is one of the biggest challenges we see with new users to the product, and how to effectively isolate the laser signal from the rest of the camera frame. Common laser calculations. There's a lot of different calculations, and it's not always clear why you would use one or the other. Some users come with an expectation from a client or from a standard operating procedure to use a certain calculation, and it may not be clear why that is. We'll go over that. And then finally, we'll get to laser profile visualizations, how to look at the data and use some of the displays in BeamGage to work with the data that you collect. One of the first features I want to talk about in BeamGage is the What's This feature. It's a really discrete feature up in the top right corner of the application, little blue, dark blue arrow and question mark. If you click that and then click any other feature within BeamGage, it will take you to the corresponding documentation in the BeamGage user guide, allowing you to very quickly find information about what you want. Almost every single feature within BeamGage also has a tooltip. If you hover your mouse over that feature, you'll get a little bit of information on what that feature does, and that can be useful as well. Note that due to some quirks with Adobe Reader, which is required for the What's This feature, some versions may require you to use that What's This feature a second time once the PDF is already open for it to actually jump to the location of that bookmark. So if it doesn't work the first time, give it another go and it'll work. There are security features you can disable in Adobe Reader to make that work more smoothly, but a second click works just fine. You can download the software on our website for free, and you can collect data and use most of the tools within BeamGage with the BeamMaker data source already built into the software. And that generates a mathematically generated beam and camera frame. Try out some of these features if you're looking to get started with our products. There's a lot of controls within BeamGage, and as a new user, it might be a little bit daunting as far as what they all do. Generally speaking, they're all there for a really good reason. It is a complex product with a lot of little features designed to solve various problems, not all of which you're going to need right from the beginning. So today we're going to break down what the most important features in the product are for you to get some good laser profile data and get some valuable measurements, which is why you wanted BeamGage in the first place. So when you start up the product, you're going to see the source ribbon. BeamGage uses a Microsoft ribbon UI. We find that it organizes content pretty effectively, and we do like it. We always appreciate any feedback, though. So as we go through the camera settings, the overall goal here is that we're trying to integrate the electronic sensor data. That charge is read out periodically from the camera as a data frame, and you're going to hear that terminology a lot, a frame. Cameras send the data frames to BeamGage, and then BeamGage does all of the analysis and image processing, calculations, and then displays all of that. So the camera does kind of a lightweight portion at the front, but it's pretty integral. If you don't set up your camera effectively to begin with, your calculations later on won't be. Also on these controls, you have the ability to synchronize the camera operation to the laser, especially in pulsed laser operations. Getting that synchronization is very important. Also, we want to be able to maximize the dynamic range available for the measurement, and then neutralize any background signals that would adversely affect the measurement. The first place to start is the frame format panel. The image format defines how much data you're going to be taking and how fast you're going to be sampling that data. So in this case, in the frame format panel, this is the default format for our SP300 camera. The full format is 1928 by 1448 pixels. That's a 2.8 megapixel sensor. It's a lot of data, but the pixels are only 3.69 microns. So really small pixels, allows for high resolution of the laser. It's also a USB 3 camera and allows frames to be output from the camera at 26 hertz optimally. I do want to point out at this point, as you're choosing different image formats, you do want to keep in mind that you're going to need a bare minimum of 10 pixels across your laser spot to be able to get a stable beam width measurement. If you have any less than that, there's just, statistically speaking, there's not enough data to get a reliable beam width measurement. So 10 is the absolute minimum, and certainly the better resolution and the more pixels you can get across your beam, the more stable and accurate that measurement's going to be. The image format tool, I'll jump back and forth. The green arrow in the top right corner of that will expand out to allow you to define a custom frame format to be able to fit your application. As you're doing that, the values that you enter will adjust and be previewed by a white box in the 2D beam display. So you can see exactly what data you're going to have and what you aren't. Along with that, especially the higher resolution these cameras tend to be. It used to be that the best camera resolution we had was 2 megapixels. With our SP620 camera that you may be familiar with. And now we have cameras that are up to 11 megapixels. There's an 11 megapixel large format camera, 6 megapixel 1-inch format. There's a large array of different cameras that you can select from. And while you may need the physical size of those large formats, you can drastically improve the speed at which you can measure and calculate by applying what's called binding. So in this panel we have, it's the same camera as before, which was 1928 by 1448, but we've set a 4x4 bin. So that means every 4x4 pixels are combined into a single pixel. And this is really great because your data size is drastically reduced. So there is a drawback of this where your effective pixel size on this camera previously was 3.69 microns per pixel. That's now only 14, almost 15 microns per pixel. The next thing within the image format that you want to make sure you have set is the pixel bit depth. What the pixel bit depth is the how much digitization there is in every pixel. So how many layers or counts of intensity are possible for each pixel. BeamGage will automatically default to the highest bit depth possible, and we recommend a minimum of 12 bits or 4,096 levels per pixel for beam profiling. There are systems out there that will measure at 10-bit or 8-bit, but at 8 bits, you only have 256 possible counts. And so your resolution, your vertical resolution on your beam just isn't really there. As far as frame rate, most cameras will already try and send the maximum frame rate possible, especially with the USB 3 cameras. They're much, much faster. And you will see that on the frame format panel in BeamGage. BeamGage will try to use all of the frames that a camera can send, but if the calculations or displays are still updating from the previous frame, it's going to skip however many frames it needs to until it's ready for that next one. So BeamGage is a consumer of the camera output, and BeamGage will try and grab all of the frames that it can. There are some competitive products that kind of obscure that. You don't really see how many frames are being dropped. BeamGage does show you this, and sometimes that actually leads to a little bit of confusion on why the frame rate seems slower. So, for an example, in this case, my SP300 model camera was set to transmit at 26 hertz, but I was only getting an effect of 7 hertz. Now, in this case, it was because I had an exposure time that was so long that it couldn't, the exposure took longer than the maximum frame rate of the camera could allow anyway. But the effective frame rate is shown at the bottom of the application on the status bar. The other major impact there is the capability of the PC. So the way that BeamGage shows you how well you're keeping up with the camera is called the subscription rate. And there really isn't a problem for most applications if BeamGage isn't getting all of the camera frames. But if that's what your application is intending, you're going to want to know how to tell if you're getting all of the frames or not. And that is this little stopwatch indicator next to the effective frame rate. If that's red, then you are missing some frames, and you might need to take some extra steps to be able to get all of the frames from the camera. Some of the things that you can do is actually turn off features and focus on collecting just the camera data, and then do your analysis in post-processing. So the next thing is the camera frame quality, and there's going to be a few different controls to do that, especially adjusting the intensity and sensitivity of the sensor to where you can get a good image of your beam profiler. And that's going to be the exposure, gain, and black level panel in BeamGage. The exposure is similar to the shutter on a film camera. It's how much time the sensor will integrate light per frame. It's ideal to set the exposure so you get a peak signal between 70 and 95% of saturation. In BeamGage, you'll see that color is going to be in the orange and the red on the default color palette, and that gives us the best possibility of getting a really stable measurement. If your laser signal is similar to the left, where that was about 10% of the dynamic range, then you're going to have a lot more variability. Some applications, that's all the signal you're going to be able to get, and there are some things you can do later on to kind of make up for that. But try and get as much peak signal as you can. BeamGage will also show saturation with an alternate color. Not shown here, but these peak pixels here would start turning white as you're getting too close to saturation. So either increase some attenuation or reduce the exposure to compensate for that. Camera gain. controls the amount of electronic amplification of the sensor signal. This is kind of like how you used to choose ISO speed of the film for film cameras, and that was how sensitive the film was to light. And it has the same effect as ISO does. Even in digital photography cameras, you'll still have that ISO setting, which is really just the camera gain. And so between the left and right charts on the bottom of this slide, you'll see that the level of the baseline didn't really increase, but the electronic noise increased heavily. And that's just between 0 dB gain and 15.2 dB gain. Whenever possible, we want to reduce the gain and not use it at all unless you really need to. The camera gain is really kind of a special feature that if you need to boost your laser signal, you can't get that signal any other way, then you can start adding some gain. Otherwise, leave gain to 0 and it'll make your life easier. So you can see the clear difference between different gain settings on this slide. Camera black level. The black level control is featured prominently with the exposure and gain controls. What this does is it sets the 0 or the actual black level of the sensor. You can see between the two charts on this slide, the baseline noise is the same in both, but it's just shifted up to 155 counts on the right-hand chart. So in this case, overall, the beam signal hasn't changed. It's just everything's been boosted up by 255 counts on every pixel. Under normal circumstances, in BeamGage, you will never need to manually adjust black level. It is set pretty prominently there, but it's just not really a feature that the user needs to mess around with. This setting is primarily used for background calibration, and we'll get into that and how that works in just a minute. For pulsed laser sources, one of the next most important features is going to be configuring your trigger source. All of our cameras have some capability of connecting to a TTL trigger source, and whatever piece of hardware is making that pulse, you're going to be able to configure that here. Different model cameras in BeamGage have different options for trigger based on the camera manufacturer and what options they support with that camera. You're going to find those details in the BeamGage user guide towards the end in the appendices, and you'll be able to look up there. If you have any questions on configuring your trigger settings after that, go ahead and shoot our service team an email, and we will help you out. One note, when you are doing a trigger-in configuration, the exposure control that we just talked about will then control the shutter integration time, and you're going to need to adjust that integration time to try and capture a single pulse of your laser if possible. And so by doing a little bit of investigating work on your pulse laser, you'll be able to adjust the exposure control to capture just a single pulse per frame. Moving on down the line on the source ribbon in BeamGage, we have the two kind of inconspicuous tools. Well, the first is lens. That one's really simple. It just does a vertical flip of the frame in software and is meant for when you use a CCTV imaging lens. This is really just for specialized applications such as viewing your laser beam on diffusing glass instead of having that laser directly incident to the camera sensor. The gamma setting is a specialized tool. It's not really used very often, but there is a really important case that you ought to be aware of that it should always be used.
These are more clean.
The gamma modifies the linearity curve of the sensor response. All BeamGage cameras are selected and tested to already have linear response in the primary wavelengths that they're meant to be used for. The exception to that is the 1550 nanometer phosphor-coated cameras. 1550 nanometers is far outside of the silicon response of a normal CCD sensor, but the phosphor coating that we apply does change that linearity, and so a gamma setting of 1.95 should always be used if you have one of those cameras. And if you ever see gamma set to anything other than that, you will be that will be a negative effect to your beam profile. So if you are working with 1550, you're going to really want to make sure that you know about that setting and keep an eye on that. So in each setup file that you have for BeamGage, that it's set appropriately. So now that we've got the overall sensitivity of the frame and we're getting some laser data, we need to talk about baseline calibration. Baseline calibration allows any ambient light and particularly electronic noise from the camera to be excluded from the measurement. That's all false signal. We don't really want that, and it will be a negative effect to your laser measurement. So there are some methods out there that will just clip the baseline off. All of the bottom signal in the camera frame in this image, they would just clip it and get rid of it. The problem with that is that tends to undermeasure the beam, and it's not really a good reflection. So we have an alternative in Spiricon products, and that is Ultracal. Spiricon's patented baseline correction algorithm called Ultracal, it helped establish the ISO 11146-3 standard for laser measurement, and has really helped set a lot of the industry in place. So some of the problems with using cameras and silicon CCDs and beam profile measurements are that the baseline or the zero level of the camera does drift over time. Silicon does respond very sensitively to ambient temperature. So as the camera heats up or your air conditioning turns on, all of those things do have a measurable effect on the silicon response of your CCD camera. The camera hardware has random electronic noise, and we want to be able to remove that. And then in your environment, you may have a little bit of light leakage or some ambient light in your configuration. And unless you mitigate that in some other way, we want to be able to get rid of that from your measurement. So is Ultracal really a big deal? I can show you why we say it is. So this is actually pretty easy to test in BeamGage, even in the BeamMaker source. Typically, when you look at just a dark frame of a digital camera, the noise floor will be clipped, like you see in the histogram on this slide. The noise is typically Gaussian, so here we're only seeing half of it. So we're missing half of the picture. So if we just clip off the baseline right now, we still have half of the electronic noise, but as the temperature of the camera changes and the silicon response changes, all of a sudden that other half of the electronic noise starts affecting our measurement. So we want to be able to get rid of that as well. So as one of the first things that we do when you enable Ultracal is that the black level, which we mentioned earlier, that will be shifted up, and you'll get all of the noise profile visible. So now it's all accessible. We know exactly what the electronic noise profile is for that camera, and now we can get rid of all of it, not just the positive bias. So once that's shifted up, we take an averaged reference frame which characterizes that noise. You'll see in BeamGage the Ultracal button gets this no symbol on it. There's also a message on the status bar saying what it's doing. And at this point, there's an indicator on the status bar that's showing whether or not it's been ultracaled. Gray means that it has not yet been ultracaled. If the Ultracal reference frame is successful and everything went well, you'll see your camera frame look like this here, where it's all purple and gray. The reason we do that, which is pretty unique, I think we're still the only products that do that in the industry. We like to be able to show you exactly what the baseline looks like, so you know exactly whether or not you've taken care of any problems there. So this purple and gray contrast shows really, really fine changes in signal. So if the bias of your baseline starts shifting positive or negative, say like your air conditioning or your heating turns on in your lab, and now all of a sudden the silicon response changes a little bit, you'll know that it's time to ultracal again. The status bar indicator will turn green. And behind the scenes, if you were to look at the histogram of that frame, you'll see that now all of the noise is still present, but because we've subtracted that out, it's equally positive and equally negative, which is exactly where we want it to be. Throwing the noise away completely doesn't really solve the problem, but having that reference frame that is now, you've neutralized the frame, any positive signal that you still have, you know is really from your laser, and that's what we want to be able to measure. So only the net positive signal after that subtraction is real. So if you were to just clip that noise profile away, you're going to be leaving all of the positive bias and not really doing an appropriate baseline subtraction. So I've already talked about how very slight changes in temperature can cause fluctuations. One story, just short story. I was working with a colleague years ago, and we were working with a new camera, and we kept seeing the signal change in a cyclical manner. There was just a cycle. It would just it would kind of bloom upward and then fall again. And we realized there was an oscillating fan running in the room, and every time it blew in our direction, the response of the camera would change. So it really is that sensitive, and in really high precision beam profiling, even somebody walking past the camera can cause a measurable fluctuation. So all in all, we recommend that you ultracal immediately prior to every important measurement. If you haven't done an ultracal in a moment, block the beam, hit it again, just do it, and that way your beam profile measurements are consistent every time because you're doing that calibration in a consistent manner. It is important to note, sometimes we see people that they're like, oh yeah, I've ultracaled, I always ultracal. But then they send us a data file, we load it up, and that ultracal indicator on the bottom is red. And what that means is that after the ultracal, they change some other camera settings, such as the frame format, the exposure, lens, anything that would change kind of what the composition of that frame was, that invalidates that reference frame that was taken during ultracal. So ultracal will automatically shut off, the indicator will go red, and if you hover over that with your mouse, it'll actually tell you what you changed to make that shut off. If you meant to do that, go ahead and apply ultracal one more time, block your beam, and then you can resume. If you didn't mean to do it, take note of what control you modified, and don't change that after Ultracal. You kind of want to get your camera settings figured out, then do your baseline calibration, then move on to measuring your beam. There are a couple other tools on the source ribbon. They're kind of quick start features is the intent. One which is auto setup. Auto setup will give you a fast, easy configuration of your exposure and gain, and then it will do an Ultracal, which also adjusts the black level, gets your background calibration done, and if your laser and your optical attenuation is already in a good place, then auto setup will just get you there, collecting data that much faster. But if you've already adjusted the exposure and gain and you're not changing those, then it's not really doing anything extra for you. And then the next feature is AutoX. AutoX is definitely a fast way of getting started using BeamGage. It'll automatically adjust exposure, gain, and black level to best suit your laser. So it's looking at your beam, seeing what the peak signal is, what the baseline looks like, and making a bunch of adjustments for you. It does not neutralize the baseline like Ultracal does, and that can add variability to your measurements. So if you're looking for just a quick up and go mode, AutoX can definitely do that. If you're looking for repeatability and precision, then you're going to want to do kind of the auto setup and the more manual configuration of the profiler. AutoX is definitely helpful in situations where normal background calibration can't be performed. And so if you find yourself where Ultracal really doesn't do everything that you need it to, then at least you can try AutoX. And if that doesn't seem to be working for you, go ahead and contact us and we'll help you out. So there are a few rare occasions where all your options that we've already talked about just haven't produced a good beam profiler. Your beam is just very weak, or there's a lot of noise. On the capture ribbon in BeamGage are some useful image processing tools. The first is frame averaging. Frame averaging does a pixel by pixel average of a set of frames. So as you increase this setting, let's say you set it to frame averaging of 5, that will take the next 5 frames from the camera, do a pixel by pixel average. So every pixel is only averaged against the same pixel through all frames, and then you get one new frame from those 5. Frame averaging is useful when the beam is stable, but the noise level is high, and has a similar effect to reducing the camera gain. It averages all that out. This does reduce your effective frame rate. So if you're seeing that your frame rate is unusually slow, but you see the averaging symbol on the status bar, then you currently have frame averaging running. It's also important to note that if you're doing frame averaging of 10, and then you stop the data source before that next frame is ready, because it was collecting frames from the camera. It got 8 frames, but you stopped the source. It couldn't complete that averaging set, and BeamGage will just back up to the last frame that did complete. So I hope that makes sense. It's just, if you don't finish the averaging set, it just rolls back one step. Same thing happens with frame summing, which is the same idea, but you are now summing the frames pixel by pixel instead of doing an average. So all of the same things apply. It reduces the frame rate, but summing is definitely a useful tool when your signal is just too low and you want to artificially boost your peak signal. So it definitely is. It's a software solution to increasing camera exposure, if that makes sense. The next is convolution. We have 5 different low-pass filter algorithms included, and if you need to have a smoothing effect applied to your frame data, then you can just certainly apply one of these convolution techniques. These do affect the ultimate frame, so you want to apply these before the Ultracal because it does change the fundamental frame. It would, if you turned on any of these 3 features after an Ultracal, it would then invalidate that. Lastly is smear correction. This is a fairly new feature that we've added to BeamGage. And there's a unusual phenomenon that happens with CCD sensors. It's always happened and it's due to the architecture of CCD design. What happens is if the signal is so intense, it passes a certain level, it can overflow the vertical shift register in that column of the CCD and cause this artificial smear in the vertical orientation of the sensor. So most camera manufacturers do, and sensor manufacturers do a really good job of countering this in the visible wavelengths where silicon sensors are designed to be used. But in the NIR wavelengths, which a lot of people use our cameras for, it still doesn't really overcome this. And one of the problems is that the sensor response, that silicon response, is so low in the NIR that you're still blasting the sensor with a lot of laser energy, which still causes the smear to happen. So while you're getting a low response to your beam, that sensor is still getting hit with a lot of energy, and that causes the same phenomenon. So NIR smearing, or the smear correction feature, will look at the top and bottom edges of the camera sensor and characterize what that smearing, that artificial smear looks like, and then it'll subtract that out from those columns. So it's a new tool that we've added, and a lot of people are finding that it does a really good job. So you're welcome to try that out. If you've been having this problem in the past, try that out in the latest version of BeamGage available on our website. So at this point, we have configured our camera. The data that we should be getting from the camera should be useful for laser beam profiling. We've configured a frame format. We figured out our acquisition mode, how we're triggering it, or if we're running CW. And we've taken care of any background calibration or other signals. And in most cases, this will yield high-quality beam profile data. So now what? If we take the data that we have here on screen, this is a really good baseline. It's all neutralized. The only signal we're seeing is from our laser. The problem is that the way the calculations work is there's still just enough noise in there that it can negatively affect the end result. These 3 frames on the right side are here. These were just 3 consecutive frames from the camera, and if just using that data, those are the 3 different, wildly different 4 sigma beam widths calculated from that data. And the only thing that's changing that you can't hardly even tell is a slight net effect of frame-to-frame electronic noise. So what we need to do is be able to exclude all of that other signal and reduce our data set down to only what's really important to us. The way that we do that is by use of software apertures. BeamGage includes an automatic aperture, which is probably the most commonly used aperture. And it's very adaptive to the current frame. It'll look at the beam, figure out where it is, how big it is, and size that appropriately. It is important to note that the ISO standards do specify that you should be doing some sort of aperturing on your beam profile data. This feature is found either on the aperture ribbon, you'll be looking for this button here, or it's always available as one of the 3 buttons in the quick access toolbar just in the top corner of the application. So we have the start and stop, Ultracal, and auto aperture as quick tools up in the top corner. So turning on auto aperture, now we see those same 3 frames. I didn't do anything else to them except turn on auto aperture. And we see that the 4 sigma widths are quite consistent between the 3 frames. There's a slight bit of variation from the left side to the right side of about 3 microns in the x-axis, well, in both axes. A shift of about 3 microns is all. The alternative, well, another tool rather, is the manual aperture. And that's where you, as a user, size and place a manual aperture on the data to choose what data is going to be included. This is again on the aperture ribbon in BeamGage. You can choose from square, circle, rectangular, or ellipse modes, and you can set the location, rotation, and the size of that aperture. And if your beam isn't wandering around, the manual aperture can do a really good job all by itself of just using that if that's what you want to do. It also has an added benefit that because it's not automatically adjusting in size by slight variations frame to frame, that it will be a little more consistent than the auto aperture. The alternative is to use both. So in BeamGage, you can enable both the manual aperture and auto aperture simultaneously. And what this does is the manual aperture works first by cutting out all of the surrounding baseline signal. It's really not useful to your laser measurement as just extraneous data. So we can use a manual aperture, this white rectangular aperture here, to just cut out all of that. And then only the data that's inside the manual aperture is then used to size and place the auto aperture, yielding in a more consistent measurement frame to frame. So typically our recommendation, unless there's some unusual circumstance, not all lasers can use both apertures. You might have some natural wander to your beam, or there's some other noise that's, from a flash lamp, for example, that makes this more difficult. But generally speaking, we prefer to use both apertures simultaneously, and the manual aperture can be placed quite consistently about where both apertures start touching. It ensures that you neither have too much nor too little data. So now that we've isolated the beam signal from everything else, and we have a consistent measurement happening, then there becomes the question of what measurements should you really use? And that's kind of a complex question, and I'll try and simplify it down as much as we can today. BeamGage collects data and performs computational analysis on more than 70 different measurement results. There's result statistics, pass-fail process control, time charting. There's a lot of features here available to you. I do want to point out BeamGage follows all applicable ISO methods for laser beam profiling. And we always indicate when and if a measurement is not ISO compliant. And those are the blue ISO tags. You'll see those throughout the application in any relevant section. So you always know if you're ISO compliant or not. And we find that we like that approach. Well, there are non-ISO kind of industry favorites that we also include. We prefer the ISO methods because they're at least an agreed upon standard, even though there's no agreed upon like calibration standard. There's no way to calibrate a beam profiler as of yet. Nobody's figured out how to prove it 100%. So at least we follow the agreed upon standards by the ISO committee. Also want to point out at this point that if you or someone on your team is knowledgeable in C# programming language, you can add your own calculations into BeamGage. They will get added into the application as if they were a native calculation. You'll get all advantage of the statistics, pass-fail, time charting. All of the features for results are available to your new custom calculation that you add into BeamGage. So if you do have some custom processing that you want to be able to do, you can do that quite simply. Contact our support group to find out more about that if you'd like to try it. So here are all the calculations that BeamGage provides. All of these can be enabled and disabled. You can start statistics without any modification of your frame data or requiring new data. It's completely non-destructive to the data to turn these on and off. I want to focus on beam width methods at first. There are 10 different varieties of beam widths enabled in BeamGage. So which one should you use? So just going over some of the list directly here, we have the 4 Sigma, Knife Edge 1090, Knife Edge 1684, which is the ISO version of Knife Edge. A user programmable. We have percent of peak, moving slit, ISO method, percent of total energy, the encircled power smallest slit from ISO, encircled power smallest aperture from ISO, and a programmable version of the same thing. If you don't already know by some standard operating procedure or a client request on which method that you want to use, it can be a little daunting to figure out what you should really be paying attention to. Each one of these can have little nuances as well, which can make it a little confusing to get started, but hopefully we'll simplify that out. The 4 Sigma method is rapidly becoming kind of the de facto standard for beam profiler measurement. The calculation integrates all of the beam data into the measurement, which is a nice option. And it is very robust with higher order laser modes. The big caveat is that it has trouble with the noise in the wings of the beam. And that's definitely apparent if I jump back a few slides here. Right here, our 4 Sigma widths, just with a little bit of noise in the wings, going across that entire frame, that was enough variation to affect the 4 Sigma calculation. So 4 Sigma requires good baseline calibration, good aperturing. You really want to get to your ideal beam profile data to get a stable and robust 4 Sigma width. Knife Edge is typically robust with various laser modes, and it does ignore noise out in the wings very well. 1090 is very popular as clip levels, but is non-ISO, which that is only really a consideration if that ISO standard and that consistency is important to you. There are definitely less popular user-defined clip levels that you can enter. It's important to note that with each knife edge clip level, you have to have a special modifier, a multiplier, that has to be input into the software. Otherwise, your results will not be accurate. And that's something that not everyone knows. There is documentation on that in the BeamGage user guide. If you're going to be using a knife edge method, you want to make sure you know about that. The moving slit method simulates a scanning slit profiler measurement. So if you're doing comparison with a scanning slit profiler, or that's what you're previously used to, the moving slit method may make the most sense to you. This sums all of the rows across all of the rows across the frame to generate one axis, just a single line profile of one axis. And then all of the columns are summed down to generate an orthogonal axis. And then the 13% of peak method is used to generate the beam width. It's really important to note that the moving slit method is only equivalent to 4 sigma methods for a TEM00 Gaussian beam or a TEM01 star donut beam. If you have any other modal content, your beam widths are going to start to diverge between 4 sigma and moving slit. Otherwise, they're highly equivalent to each other. So again, that's important to note that if you're doing comparison between a scanning slit profiler and another beam profiler, whether it's BeamGage or a different one, you really need to be using the moving slit method. And then if it's not a TEM00 or TEM01 star, there's going to be some natural deviation between those two products. They just aren't going to be equivalent. With the ISO standard encircled power methods, the smallest slit method simulates an adjustable slit on the centroid location of the beam, and then that's sized smaller and smaller until they find 95.4% of the total beam power or energy. This is also called the power in a bucket method, and it's important to note that that only measures beam widths. If you need a diameter result from that, it does not do that. The encircled power smallest aperture measures beam diameter only, not widths, along 2 separate axes, and that simulates an adjustable iris at the centroid location to find 86.5% of the beam power or energy. The non-ISO methods, percent of peak, 13.5% of peak is probably the most popular in my experience. It's also called 1/E² method. 50% of peak is also called full width half max. So if you're used to that term, then to get full width half max in BeamGage, all you have to do is set a 50% peak clip level, and you'll have it there. We don't have it listed separately because it's just a modification of that clip level. So if you're looking for full width half max, it is in the product, and you just have to set that clip level. And percent of peak only measures data down a row and a column along orthogonal axes. So it's not considering all of the data. Sometimes that's a really good benefit, though. If you're using percent of peak, it's not wrong to do it. It's just different. It's a very different method, and is kind of the original standard in a lot of fields. So there are a lot of people that use percent of peak. Percent of total energy is probably used a fair amount less. That measures a sample width and kind of does a first pass width, and then determines how much of the area of the beam, which includes your clip level percentage of the total energy. It's important to note 86.5% of total energy should yield an equivalent beam width to 13.5% of peak method. Even though computationally they're doing a different algorithm, they end up with equivalent results between those two. Percent of total energy is good with if you don't have a lot of extra signal in the frame, because all of that's going to be counted towards the total energy, and that can yield to some errors in your measurement. Before I move on, I didn't really answer which beam width method you should use. You should use the one that's most appropriate. If you have a preference to one, there's nothing wrong with that. We provide those all for those reasons. But if you are new and you don't really know what you want to use yet, 4 sigma is definitely a good standard. And there are cases where 4 sigma is not a good choice, but try 4 sigma, see how well it works for you, and then you can always move on from there. Other calculations provided in BeamGage are the power and energy result group. These are really good in making comparative measurements between data samples, and can also be used to make relative power measurements. This uses tools that are on the computation ribbon. You'll find this power energy panel on the computations ribbon, And by measuring with a standalone power energy meter, you can then input your calibrated power and your power units, and then apply it, or your energy value and energy units. Apply the calibration, and all of your power energy results are now relatively adjusted to be shown in power or energy units instead of camera counts. If you're doing divergence measurements, there are 3 different methods included in BeamGage: the ISO divergence method, the far field wide angle method, or the far field 2-point method. This requires additional procedures that we won't go over today, and the tools for doing that are also located on the computations ribbon in BeamGage. Definitely look up in the BeamGage user guide for exactly how to use those. They're relatively simple, though. If you're familiar with those methods, the controls should make a lot of sense. If you're working with top hat laser beams, we do have a top hat result group. Contains all of the ISO top hat calculations. These are very helpful in identifying the effectiveness and consistency of a top hat laser when it's really doing work. So whether it's how flat or uniform it is, or how sharp the edges are, it really helps characterize where all of the energy is and if that's being effective at doing work. If you're working with Gaussian lasers, we do have a full set of Gaussian results as well. ISO has removed the goodness of fit measurement from the standards, and they're working on trying to find a suitable replacement. At this time, the goodness of fit calculation that we've included is our interpretation of the goodness of fit as it previously was included in the standard. And there are common other Gaussian calculations as well. And this will do a standard Gaussian fit on the data that you supply to BeamGage, and then do those calculations. Typically, the Gaussian calculations are computationally expensive, and if you're trying to do these with one of our large format cameras or at higher frame rates, you will notice a performance drop, and that's just hard to avoid, being what they are. So take note if you're trying to use some of those and you do see a performance drop. We know. It's kind of hard to avoid that with those calculations. In BeamGage, there's also kind of a lesser known feature, but it needs to be, it's a very important feature, and that is your beam width basis. And what this is really kind of the referenced beam width, which drives a bunch of behavior for some other features within the application. So whether it's an ISO calculation that requires a preliminary beam width, or it's driving like beam width indicators in the beam displays, this control sets which beam width calculation will be used to do that initial calculation. Note that this does not prevent you to be able to calculate all beam widths. BeamGage, you can enable all of them simultaneously, independently of every other feature. So don't think that by selecting 4 sigma that you can't do a percent of peak measurement simultaneously, as BeamGage handles all of that and runs those concurrently. Optical scaling may be a feature that you need in your application. If you're using any sort of imaging lens or magnification or reduction optics, then you're going to want to be able to scale all the spatial dimensions to account for that optic. So if you have like a reduction telescope or a magnification telescope and it has a calibrated magnification value, all you have to do is enter that value into this control. BeamGage applies this correction at the pixel dimension level, which then propagates out to every feature from there. So by entering it in one place, every feature in the application will automatically scale to your magnification that's being used in your application. And that feature is on the computations ribbon. At this point, we've gone through setting up the camera, getting good data, working with the different calculations. And the last is how to visualize the data. And then there's some other little tools that we have with those beam displays that are useful in working with the data, you know, kind of from a human perspective, where the calculations is working with it, you know, from the computer's perspective. Most common is the 2D beam profiles with the CCD array intersecting the beam. Most people want to see that two-dimensional image of what the beam looks like at that cross-section. There are several features that are in the beam display ribbon of BeamGage that allows you to customize some of the behavior. The cursor is a tool on the beam display. The cursor is enabled by default in BeamGage and is this dotted X and Y line. It goes all the way across your data and is selecting orthogonal slices of data, a row and a column. It tracks centroid by default, but you can also change that to track the peak location or just have it manually selected at an arbitrary location of your choice. The cursor is the feature that selects the XY data for the 1D profile displays. So if you're trying to work with the 1D display windows and you're not getting any profile data, make sure that you've enabled the cursor. The crosshair controls right next to the cursor controls it's an indicator and a control that's selecting a single XY point. You can set this to track centroid location or peak location, or to manually select an arbitrary point. And then these two features can work together to perform linear distance measurement. If you're trying to look at two features within your data, enable both of these. And then in the spatial results group, there's a cursor crosshair result, which will give you the distance between those. And we also provide a centroid crosshair result, as that's very common in users that are using multiple beams. They want to look at each of the crosshairs and find out you know, the distance from the centroid. Also in the 2D profiles, one feature that I've seen confuse people at times, and it's these white 1D profiles on the left and bottom edges of the 2D display. What that is it's a reference overlay of the 1D profile data. So this is the 1D profile. The x-axis of the cursor is shown on the bottom of the 2D beam display, and the y-axis of the cursor is then transposed over to the left side of the display and gives you an instantaneous view of the intensity profile at that cursor location. And that can be enabled and disabled. If it's not useful in your application, go ahead and shut that off. And that's just on the beam display ribbon. Some applications require a different origin location than what's default in BeamGage. The default is bottom left. And that origin location is shown as a small red circle, same as the circle that's on the control, to give you a helpful clue there. And typically you'll see that down in the bottom corner. In this view, it's zoomed in a little bit so you don't quite see it, but it is just a red circle in the bottom left corner by default. Options for that are to set it to the center of the frame, or you can use the crosshair tool, pick an arbitrary location where you want the origin of your data to be, of your XY data, and then use this control to set it to the crosshair location. So, and that'll transpose all spatial calculations to now reference a new origin location in the XY coordinates. So we mentioned the 1D profiles previously. Aside from the 1D overlays in the 2D, you can also just pull up a full 1D beam profile chart for both the X and the Y axes. And so again, what we're looking at is the data along the two cursor lines transposed into their respective charts. The controls for the 1D beam profiler are located on the beam profile ribbon. By default, the solid blue line that you see in the profile is a movable cursor, and the intensity value and location of the cursor on the sensor is displayed at the top of each beam profile window. There's a separate window for both the X and the Y. You can enable a beam width indicator. It shows up as dashed red lines. So this is where that beam width basis setting comes into play. Whichever beam width method you have selected will be displayed here by the red dashed lines to give you a quick at-a-glance view of really where the measured beam width is. If you're working with Gaussian fits and apply a Gaussian fit to your current frame, you can then enable a Gaussian fit overlay onto your 1D beam profile to easily see how close to an ideal your current laser is. While you apply the Gaussian fit to the current frame in the reference subtraction panel, in this case you would not want to apply the subtraction, as that'll then change the blue beam profile in this view. So you can do the Gaussian fit without doing the reference subtraction. A linear caliper tool is also available, and that pops up a second solid blue cursor line, and then the span is automatically measured between those two cursors, and the little X's that you can see on the profile data are the point along that profile that's currently selected. That information about the intensity and location of each cursor is provided at the top of each window. For 3D profiles, BeamGage combines the X and Y data along with the intensity data to create a spatially accurate three-dimensional view of the laser. For this display, a dedicated graphics card will dramatically improve the performance of the 3D beam display, but will also improve the performance of other BeamGage, the rest of the BeamGage user interface, as it natively uses graphics capability if you have it. We recommend, as a default, any BeamGage users should have a dedicated GPU for normal use of BeamGage. And this really streamlines and separates the display updates away from the computational updates, and allows BeamGage to perform better overall. On the beam display ribbon, there are controls provided to be able to pan, zoom, rotate, and tilt the 3D view. There are also mouse controls provided, be dragging left or right or both mouse buttons. You can easily zoom with your mouse wheel. Same thing, you can also zoom using your mouse pad if you don't have a dedicated mouse. On the 2D or 3D properties panel, the 3D resolution can be customized. This setting effectively bins. We talked about binning the camera data before, but this setting bins the 3D model. So there's less data points to draw, or dramatically improving the performance of it. By default, we set it middle of the road at 5. That's essentially a 5x5 binning. If you set it to a value of 1, that'll be a full resolution 3D model. It'll be very graphically intensive, but it can be done. And just note that when you set it to 1, everything slows down. That is why. If you don't really need the resolution, but really want an at-a-glance 3D view, You try setting that up to the maximum of 10, and you'll get a low resolution but a really quick 3D view of what your laser is doing. Additionally, BeamGage provides an ISO-compliant beam positional stability monitoring tool. It will plot the centroid locations in a spatial histogram chart, and interpreting this chart is as easy as referencing the color levels on the right-hand side. This shows us that the peak color, the white pixel here, has had 69 counts. So the centroid has landed on that location 69 times, and then it scales down from that, from whatever the current peak was. Provided in that window are all of the ISO standard beam positional stability measurements. So in summary, we've identified the common camera settings. We've learned how to use those. We've learned common tools necessary to acquire laser profile data that's actually effective and gives good measurements. We've learned how to isolate the laser signal from the rest of the data, looked at different laser calculations, and looked at how to use some of the different beam displays to work and view that data in a way that makes sense for humans. There is a full automation interface for BeamGage, and most features, the features that we feel make sense for automation, are included in those APIs. BeamGage is developed and tested in Windows 10 and Windows 7. Soon Windows 7 support will be dropped by Microsoft, and we will probably follow suit with that once it's no longer officially supported. In a production environment with a lot of ambient light, does that affect Ultracal? It does and it doesn't. So Ultracal is really excellent at identifying and characterizing any static signal that needs to be taken out. If that signal is changing, like somebody walking past the camera, or it's really amazing how much light intensity the shadow of a person is in a laser lab. Just walking around the room, you might be surprised at how much that fluctuation you see from that. If possible, some of the techniques that I would use is often I'll put like a 3 or 4 inch C-mount tube on the front of the camera. If you have enough room, just putting a tube like that, an extension tube, can prevent a lot of that ambient light from getting in there. The other thing is providing enough optical attenuation to the point where those ambient light levels are essentially they're mitigated by the attenuation. That's another way of compensating for it. So BeamGage will recognize any camera that we've integrated. It does not support purchasing, a third-party camera. The cameras do have an embedded license for our software, but it automatically will recognize the cameras. So on the source ribbon, there's a local detector button, and clicking that button will enumerate any camera. So in this case, I have 3 different cameras currently connected. Our in-gas SP1203, our high-resolution in-gas camera, our large format 35 millimeter camera, and our 2.8 megapixel CCTV camera, the SP300. So if you've installed the drivers for that for each camera during software installation, and you have those connected, clicking one button will find all of those cameras. So once again, if you have any other questions, go ahead and email us, our support team, at service@us.ophirop.com. we will help you out with any additional questions. Thank you very much for stopping by today and giving me your time. I hope it was productive for you.